Right, ready? So, good morning all of you. The summary of the last lecture, we have started this 1D monoatomic lattice. That means we are discussing the discrete nature of the lattice, how it behaves whenever you are sending an electromagnetic wave of certain frequency, how it behaves. So what is the conclusion from the yesterday's class? Our discrete nature of the lattice is not sensitive for the lower frequencies. So that means no use. We are not getting any dispersion. We are not getting any interaction. Simply it is passes through that. That's why no use. Now let us go for the another one. Are you ready? In the last class, we have already derived the dispersion relation under root 4 beta by m sine Ka by 2. This was the December 2013 CSIR question. Which of the following is the dispersion relation for 1D monoatomic lattice? But they have given 2 omega naught. 2 omega naught sine Ka by 2. That means 4 is out, 2, and root beta by m they have taken omega naught, nothing else, 5 marks. Ready? So, and one more relation we have given for this in terms of velocity of sound, 2 Vs by A sine Ka by 2. So, I hope you check that next condition. Okay, anyhow, let me. Next case, we are taking at a higher frequency. At a higher frequency. So, higher frequency means it's a short wavelength or long wavelength? Short wavelength. So, short wavelength means lambda tending to 0. That implies K is not tending to 0. That is why we cannot neglect here. So, omega is as usual under root 4 beta by m sine Ka by 2. We can't take any approximation because the theta is very high. So, okay, again I am taking, I am finding this phase velocity, and let me check whether there exists a dispersion or not. Phase velocity equal to how much? 1 by k under root 4 beta by m into sine Ka by 2. Babu, important, please listen. And the next, here I am finding the group velocity, which is equal to d omega by dk. I think this can be written as 4 beta by m under root cos Ka by 2 into. So, in the last class, whenever you are dealing with the lower frequency of EM waves, we got Vp and Vg both are same. That is why we conclude there is no dispersion. But here it is not like that. The group velocity and the phase velocity both are not same. Whenever both are not same, what is this? There exists dispersion. Means this 1D monoatomic lattice, 1D monoatomic lattice acts like a dispersive medium, acts like a dispersive medium for which frequencies? Yeah, for higher frequencies. So that means what? It is allowing, and some dispersion also exists. Okay, it is allowing some frequencies. It is allowing some frequencies. That's it. Okay. And now let us see what is the maximum possible frequency. What you are saying, it is allowing frequencies and there exists dispersion. Now we have to check with this dispersion what is happening and what is the maximum possible frequency it can allow. I told you in the last class a small point. This acts like a low pass filter. That means it will allow only those EM waves whose frequency is less than a particular frequency. Are you ready? Let me find those things also. Now listen. Okay, so here we would like to find what is the maximum frequency. Maximum frequency allowed. Very important. Allowed. Once again I am taking this omega. Omega equal to under root 4 beta by m sin Ka by 2. 1 minute. What do you want? Omega maximum. We want omega maximum. Up to this I hope everybody understand. Just we have shown that there exists a dispersion. That means it acts like a dispersive medium for a higher frequency. So it is allowing certain frequencies, no doubt. But what is the maximum possible frequency? That is what we are finding. Omega max you want. And this is a constant. Then whether it is maximum, minima, it depends upon the sign value. Can you please tell me what is the maximum value of sine? 1. Say yes or no? And one more thing you forgot here. Modulus. Because it should not be negative. Okay, fine. So this entire value should be equal to plus 1. That implies, I hope everybody got it, the modulus sine of Ka by 2 should be equal to plus 1. Now I am going to find for what values of K we are getting this maximum. Okay, are you ready? So, okay, so that means, come on, K A by 2 equal to N pi by 2 plus or minus pi by 2 plus or minus 3 pi by 2 plus or minus 5 pi by 2, so on. Why plus or minus? Modulus. This implies 2 gets cancelled. K equal to plus or minus pi by A involve, otherwise you won't get interest and you won't understand also. Involve. Oh, at all these values of K you are getting omega maximum, and it is allowing some frequencies up to a certain maximum value, and that maximum value exists at which points? What are these? Zone boundaries, Brillouin zone boundaries. So these are nothing but Brillouin zone boundaries. Cool. So in this discussion what we understand, the maximum frequency exists at zone boundaries, Brillouin zone boundaries. Now let us see what is that value. Yeah, it's very simple. So omega max, we already said this is equal to 1. Could you please tell me how much it is? Up to this any trouble? Come on, make it fast. Just I find where it is maximum and how much it is. To the zone boundary, it is allowing frequencies, and the maximum value exists at that zone boundary. Means something is happening at the zone boundary. What is happening? Let us discuss. Sorry. If you already studied all these things from the textbook, you feel a little bit comfortable. But most of you, I don't know, after the class I told you to study for 1 hour and most of you people are going. That means you are leaving the subject. The subject will leave you. Shall I tell you the best thing while you are taking coaching, any coaching, before coming to the class, that topic you have to read and come. Then only you will get 100%. But that much time is not there. They will give homework unnecessarily. Ready? Fine. At higher frequencies we are getting the dispersion phenomena and it is allowing certain frequencies, and the maximum frequency that can be allowed is under root 4 beta by m, and that too, that maximum exists at zone boundaries. That's interesting. It's very interesting. Listen. Okay, so omega maximum exists at zone boundaries. Now let us check at zone boundaries what is happening. At zone boundaries. So zone boundary means k equal to, I think you know, n pi by a plus or minus n pi by a. Now with your permission, I will take the group velocity. Group velocity equal to d omega by dk. Already that we have done already. So please tell me how much it is. A by 2 under root 4 beta by m cos ka by, wait, I am going to find that group velocity at the zone boundary. That means the group velocity at a zone boundary, Could you please tell me, if I take n pi by a and substitute here, a gets cancelled, answer? Sure, pakka. Once again, k is n pi by a gets cancelled, cos pi by 2. That's why this is equal to 0. Oh, goodness. So, if you take a 1D discrete lattice at a higher frequencies, that means whatever the wave you are sending, it is having a higher frequency range. If you are sending that electromagnetic wave, how it is behaving? Up to zone boundary, it is allowing the frequency. Up to what is the maximum possible allowed frequency? Under root 4 beta by m. At a zone boundary, what is happening? Group velocity become 0. For which wave? What is the meaning of group velocity 0? Group velocity is nothing but the rate of energy transfer. Maybe I have explained in the quantum mechanics. The amount of rate of energy transfer is nothing but the group velocity. The rate at which the energy transfer, momentum transfer is nothing but a group velocity. Because a disturbance created in a medium which can transfer the momentum or energy from one place to another place. So what it is carrying? Energy, momentum. That velocity is nothing but the group velocity. So here group velocity become 0. That means, does it carry any energy? Oh, it's not carrying, it's not transferring any energy. Then which wave it is? So at the zone boundary, your wave become what? Which waves are? Energy spectrum wave. Energy spectrum. What you are studying is a phonon spectrum. So that spectrum become what? A standing wave. Let me discuss. So group velocity equal to 0. That means what is happening at zone boundary? At zone boundary. So it behaves like a standing wave. A standing wave. Why it is a standing wave? Group velocity 0 means any transfer of energy? No, no transfer of energy. Sir, I didn't understand what is happening here. Yeah, I am going to explain here. See the diagram. Okay, now we are talking about the higher frequency electromagnetic waves. That means this is my reciprocal lattice. Everyone please observe, very important. This is my k axis, and here I am taking the spectrum, energy spectrum, that means omega. Is it okay? On this I have taken k, and here I have taken omega. Ready? So this is the 0, and here I have plus pi by a, and here this is minus pi by a. So this we can take it as a first Brillouin zone. What is that? In the earlier classes I told you, you will be having a first Brillouin zone. It is surrounded by a second Brillouin zone. No doubt, somewhere here plus 2 pi by a, and here also minus 2 pi by a. Wait a minute. I hope at least some of you have seen this diagram in the textbook. Have you seen? Right. Now let us see what is happening. We are studying at higher frequencies, right? Okay. So, ready. At higher frequencies, we have not taken any approximation. That's why omega, dispersion relation, under root 4 beta by m sine. Ready? Now, let us suppose at k equal to 0. Put k equal to 0, omega equal to 0. Then where is the point? Here. Okay, now that means at k equal to 0, your omega equal to how much? 0. Now just now we have seen one more thing. At zone boundaries, we are having a maximum. Say yes or no? So one more time. At k is equal to plus or minus pi by a. I have taken first Brillouin zone. Now omega is maximum or minimum? Maximum. How much it is? Are you observing? Oh, at the zone boundary it is having a maximum value. At the zone boundary it is having a maximum value. So 0 to maximum, 0 to maximum. Okay, sure. Now few minutes back we have discussed, at the zone boundary it is not allowing any other wave which is greater than this maximum. That means how much it is? Under root. If it is allowing further energies, so this wave will go like this. For example, it is allowing all the frequencies, then it will go to infinite. Are you understanding? But what is happening? It is allowing only up to, and that too at zone boundary it behaves like a okay. So it's becoming like a standing wave. So from this frequency it is not allowing any other waves of a frequency is greater than this, and at this zone boundary what is happening? It become a standing wave. Is that clear? Wait a minute. Good. Okay, so we got this. Fine. From that graph, what you are understanding? Now carefully observe. Ready? Now I am taking This is the first Brillouin zone I have written, and what is this ma? A second Brillouin zone, and this is also what ma? Second Brillouin zone. Say yes or no? Carefully observe. I hope everybody understand the diagram. So what is happening at k equal to 0, it's 0. At zone boundary maximum, just I have drawn the graph, and at zone boundary it is becoming a standing wave. It is not moving any further because it is not carrying any other frequency greater than this. That's why it is becoming a standing wave. Good. Now all of you please see the first Brillouin zone. This is the left side or right side? This is the left side of first Brillouin zone. Say yes or no? Yes, now everybody see this. Is it a second Brillouin zone or first Brillouin zone? That to right side or left side? Right side. This is the right side of Brillouin zone 2. Now carefully observe both. The left side of first Brillouin zone resembles or quite similar to right side of second Brillouin zone. Next one. See this part. Right side of first Brillouin zone, and see this part. Left side of second Brillouin zone. I am not writing any sentences. I am not giving any points. I hope you understand. What I want to say is, one part of first Brillouin zone resembles the one part of second Brillouin zone. Similarly, the other part of first Brillouin zone quite similar to the other part of second Brillouin zone. What does it mean, sir? Means you need not to bother about all the Brillouin zones. It is enough to study only first Brillouin zone, because once you got the properties of first Brillouin zone, you are getting the properties of second Brillouin zone also, quite similar to third Brillouin zone also. I don't know how many of you understand this point. So your second Brillouin zone resembles the first Brillouin zone. Similarly, third Brillouin zone resembles all resembles first only. For example, this will be in the third, right? Now see, this will be in the third. So this is shape where you have here. I hope you understand what I am saying. So that means what? This is called what is that? Extended Brillouin zones. That means we are having so many Brillouin zones. We can't study each and every Brillouin zone what is happening, but the God created this. That means you don't worry about other Brillouin zones. Whatever the first Brillouin zone you got, the same characteristics and the same properties repeating in the second Brillouin zone, third Brillouin zone, like that. That's why we always study the crystal properties only within the first Brillouin zone. That is a Wigner Zeit cell in reciprocal lattice. You understand this point? First write down. If you want, I will give some point. So it acts like a low pass filter, and why I have given the reason, you know, just write those points. As omega less than omega max, lattice behaves like a dispersive medium. It is allowing certain frequencies. But omega equal to omega max, no transfer of energy through the lattice. That is why a 1D monoatomic discrete structure acts like a atomic lattice, a discrete, acts like a low pass filter. The higher order Brillouin zones, the higher order Brillouin zones, that is the second, third, so on, resembles the properties of, resembles the first Brillouin zone. That is why it is enough to study, it is enough to study the properties of, it is enough to study the properties of for first Brillouin zone. So no need to bother about all the Brillouin zones. You just study the properties of first Brillouin zone, because the higher order Brillouin zones resembles the first Brillouin zone. So that is the most important conclusion we will get from this study of 1D lattice. Really 1D lattice exists? Can you give one example for 1D lattice? If I say, maybe you will surprise, DNA. DNA is a 1D lattice. Your DNA. Huh? What is DNA now? 1D chain lattice. That is it. So we got these points, some interesting points we got from this 1D monoatomic lattice. Although derivation, whether you understand or not, but the conclusion points you must remember. So 1D monoatomic lattice is not sensitive for the lower frequencies. So it is used for only higher frequency of electromagnetic waves. That's ready? Yeah? And what is the maximum possible frequency you can allow, I mean it can allow through this lattice, under root 4 beta by m, and that too, that maximum value exists at what? Zone boundaries. At zone boundaries, what is happening? Group velocity becomes 0. What does it mean? It behaves like a standing wave, no further transfer of energy. That's it. And the most important thing, once you have drawn that structure Brillouin zones, what is happening? The higher order Brillouin zones resembles the structure of first Brillouin zone. That is why it is enough to study the properties of first Brillouin zone. Every interview you will face one question minimum, worst case. Definitely you will face one question from the materials, because during your research definitely you will study or you will work on the materials, no doubt about it. I told you to study at least 1 hour and go. First few days studied. But the winner is only the person who is carrying till the end. Some people will drop in the middle. Those are idiots, useless fellows. And some people only will carry it forward up to the last. Those are the winners. Very few members will be there. They will start, I told you already, three type of students, 3 category of students will be there. Some people won't start, some people stop and drop in the middle, some people carry forward till the end. The winners are those 3rd category. First category is better than 2nd category. Why? First category, he will leave this coaching and he will go for some bank post or something like that. Something. But the 2nd category can't do anything. Ready? Ready? Right. So this is what we get from this 1D monoatomic lattice. Now let us change this structure. Are you ready? Now I am taking again 1-dimensional diatomic. Very important this one. Diatomic, 1D diatomic lattice. So here I am taking the 2 atoms. Okay, all of you please listen. So the number of atoms in this unit cell here, how much? 2. That's why, is it a Breve lattice? No, it's not a Breve lattice. Very few people are responding. Is it a Breve lattice? Why it is not a Breve lattice? Are you interested? No, not a Breve lattice. It's not at all a Breve lattice. Okay, fine. Let me take the structure. So here I am taking the lattice points, something like this. Now here I am considering the diatomic. One atom mass is m and another atom is capital M. Now I am assuming these lattice points I can take like this. This is the even lattice points. That's why this is odd, and this is also odd, and this will be even, and here again even, something like this. Is it okay? Now I am considering at even lattice points you have small m, at odd lattice points you have capital M. That's it. Okay? And each, the lattice parameter is A, that means it is a coupled. Springs means it indicates there is a coupled oscillations, or one atom disturbed, all other atoms also disturbed, something like this. And I have taken the parameter as A. That's it. Okay, cool. Now here I have 2 types of atoms. First one I am considering atom at even lattice points. Very simple, already, because in the last class we have discussed quite similar thing, nothing else. I am taking this. This is a 2n, and here you have 2n plus 1. Here it is small m. Here it is. You are not saying. And this is 2n minus 1, and this is capital M. So this displacement is u2n. This displacement is u2n plus 1. And this displacement u2n minus 1. If you remember what we have done in the last class, the force acting on this even atom equal to beta into u2n plus 1 minus plus u2n minus 1 minus, very good. Is that clear? Quite similar one. And this can be written as m, mass into acceleration, d square. Its displacement is u2n by t square. Any trouble up to this? No. Next, quite similar to that, I am taking atom at a odd lattice point. At a odd lattice point. Let us do it fast. So here we have odd lattice point, capital M. How much it is? 2n plus 1. And this is 2n plus 2, small m. And this is 2n, which is small m. And again I am taking the same displacements. This is u2n plus 1. Similar algebra, that's why I am doing fast. 2n plus 2. If you 2, that's it. Now again I am writing the Hooke's law, that is the force acting on odd equal to beta into super, very nice. And as usual, this is nothing but MA, but here it is capital M, d square u 2n plus 1 by, that's it. Okay, fine. And everybody know this is a SHM equation, Hooke's law. That's why I am taking the solution u2n. I am taking the solution. So this is u2n equal to, I am giving the amplitude for small m as a capital A. Okay. So that's why capital A e raised to I omega t minus k. Shall I write directly? Or shall I have to write x or something? Everybody understand? Good. So this is even. Similarly for all even atoms, I hope you understand, 2n plus 2, 2n plus 2, 2n minus 2, whatever you want. Can you write? That's good. And this is also SHM. I am taking the solution. So this is u 2n plus 1, odd or even? For odd atoms, I am taking the amplitude as b. Ready? So start. This is a b e raised to I into a. Any trouble? So that's it. And we got the even atoms solution as well as odd atom solution. First I will take this, and similarly we can do this. No need to do both the derivations. One is enough. So I would like to take this. Then I want 2n plus 1, 2n minus 1, 2n. I have 2n already. What I want? 2n plus 1, 2n minus 1. Both are odd. That's why let me write this small note. I want u 2n plus 1. Oh, it's not there. It's there. It's there. So how much it is? b e raised to into e raised to minus I k a. Check. Once again. So u 2n plus 1 equal to this one. Okay now. So please write b e raised to I omega t minus 2 k n a into e raised to minus I k a. Okay. Now similarly one more thing you want. What do you want? u 2n minus 1. u 2n minus 1. Ready? Start. b come on. Into. Up to this any trouble? Come on, start. Make it fast, make it fast. Because no need to explain again and again. Already we have done yesterday the quite similar one. Remember, first one we have taken Debye lattice. Now we are taking a not Debye lattice. Yesterday we discussed one atom. that is the Debye lattice. After this, don't stop. Please take the first equation and substitute whatever you got, u2n plus 1 and u2n minus 1. Please substitute. Don't waste the time for others. Just write the Hooke's law and write the solution of SHM sinusoidal. Over. After that, take the small m equation, that means even lattice points Fm, F small m equal to beta into u2n plus 1 plus u2n minus 1 minus 2 u2n. And what is Fm, you know, that is a mass into acceleration. I hope once you have differentiate 2 times, you know what you will get. Yesterday you have written un, today you are writing u2n, nothing else. For understanding the result, we have to do the mathematics, otherwise We don't know what is happening there. Simply I will say atoms are moving in out of phase. How do you know? For that we are doing all this algebra. Over? Ready. So I have taken this even atoms f small m, and I hope this is the equation. Mass into acceleration. Once you have done 2 times differentiation, what you will get? M minus omega square u2n. Wait, stop. I am substituting minus m omega square u2n equal to, everyone see, beta. This is a u2n plus 1. All of you please listen carefully. This is u2n plus 1. Already you know what is a u2n plus 1. Just write that b e raised to I omega t minus 2kNA into, good, slowly, plus, you know what is u2n minus 1, b e raised to I k. I think you also will write the bracket. Yada sar thada students. Right. Minus 2 a e raised to I omega t. Say yes or no? Okay. So what I am doing is, okay, fine. And you know what is mu 2n again? What is mu 2n? A e raised to I omega t minus 2kNA. If you observe carefully, everywhere cancelled. Then what's the remaining here? Minus m omega square u2n capital A equal to, this is a beta. Shall I take b common? Okay, I am separating that. Minus 2 beta A. Is it okay? Any trouble? Now, this is something is missing. What is missing? Into, finally, minus m omega square A equal to, ready, 2 beta B cos minus 2 beta A. Any doubt up to this? Now you need not to do the next one. Ammaya. So similarly for odd lattice points. Simple. In the place of small m you will get capital M. In the place of A you will get B. In the place of B you will get A. Nothing else. Come on, start. That is small a. Minus 2 beta. That's it. So these are the 2 equations. Okay, cool. Now let me write in a format, proper format. So here I can bring this term this side, then I will get 2 beta minus m omega square capital A minus 2 beta cos Ka into B equal to 0. Similarly, second one also I am writing in this format. If I bring this term this side, 2 beta, come on, 2 beta minus m omega square into B. Next one, ready? Is it plus or minus? Next, bring this, minus 2 beta cos K into what? Equal to 0. Okay, ready? So here you got 2 equations with amplitudes A and B. What you are doing here means, what you are doing? You are trying to find the relation between amplitudes. How that atoms are vibrating, because 2 atoms you have. So first we have to know how they are vibrating. At the same time, you are going to find what? Dispersion relation. What is the meaning of dispersion relation? Omega. Ready? What is the trivial solution for this? Trivial. A and B are 0. Trivial solution means 0 solution. For example, 2x plus 3y equal to 0. Another ax plus by equal to 0 I said. Trivial solution is x is 0, y is 0. Non-trivial solution not equal to 0. Then determinant should be 0 at the point. Okay? Right, listen. So here I am taking for non-trivial solution. Trivial means 0 solution. All are zeros. That is called trivial. So non-trivial solution. For a non-trivial solution, that means A and B are not zeros. If I take A and B are zeros, then there is no wave. That's why I should not take A and B 0. That's why I am using the word. That means the determinant equal to 0. Are you observing? Now this implies, come on, say the determinant. Equal to, find the determinant. Find the determinant and you will get an equation omega power 4 in terms of omega power 4. Come and do it. Just a small determinant, multiply. At least you multiply that. After that I will explain. Multiply and tell me what is the final expression. 5 terms you will get. Just find those things. Four beta square minus 2 beta omega square, I think m plus small m plus small m and capital M omega power 4 minus 4 beta square and write it as 1 minus sine square Ka. I hope please check after replacing cos square theta as 1 minus sine square theta whether you got that or not, please check. Because 2 terms gets cancelled, 4 beta square, I think. Simplify, simplify. Easy mathematics, not at all difficult. Let's proceed. please substitute cos square theta as 1 minus sin square theta, and 4 beta square cancel, and please write omega power 4 plus something, whatever the remaining you please write down. So I think this 4 beta square gets cancelled, and finally what you get, small m capital M omega power 4 minus 2 beta omega square capital M plus a small m minus of minus plus 4 beta square sin square Ka equal to 0. All of you got this? Now divide with the small m capital M. Just divide with the small m capital M. Omega power 4 minus 2 beta capital M plus a small m by small m capital M omega square plus 4 beta square by small m capital M sin square Ka. Finally, you got a quadratic equation in terms of omega square, If you copy that also, waste Babu, no use at all. Just take a common, that will be cancelled. After that divide with a small m capital M. Finally you got omega power 4, how much? Minus 2 beta 1 by small m plus 1 by capital M. Say yes or no? Please check. Omega square plus 4 beta square by small m capital M sin square Ka. Right. So this is nothing but omega square whole square. That's why it's a quadratic equation in terms of omega square. Then the roots omega square equal to minus b plus r minus root of b square minus 4ac by 2a. Come on, do it. Everything you know. What is a? 1. What is b? This one minus. What is a c? This one. Come on, school level algebra. I think finally if you substitute, please check whether you got this or not. Babu, if you directly write this without doing, no use, you won't remember. That's the main problem, main issue. Please check whether you got this or not. It's a quadratic equation, do it yourself. How much after that? Minus 16. Oh, common 4. 4 beta square by small m capital M. Am I right? Huh? Beta na beta square? Beta square. Sin square K. Please check. This is the dispersion relation for 1D diatomic lattice. Check. Beta square is not there. Oh, taken common. Okay. That's why do it yourself. Don't copy. Sir will do mistake. Don't copy. Do it yourself. What is here? 4 amma. Just minus b plus r minus root of b square minus 4ac by 2a. Once you simplify, you get this. Right. So what is this? This is the dispersion relation. Of what is this? 1D diatomic. 1D diatomic, is it a discrete or a continuous? Continuous. So we will treat it as a continuous structure. Yesterday I told you one statement. While you are taking the approximations, either you can take a first approximation, second approximation, like that. Sir, what is the meaning of a first approximation? Right, listen. Sin theta equal to 0. Then your cos theta must be 1. Sin theta, if you take theta, then cos theta must be 1 minus theta square by 2. Understand what I am saying? So whatever you want you can take, no issue. But remember, while you are taking the approximation at larger frequencies or lower frequencies, whatever it is, omega should not be 0. For example, sir, first approximation I got 0, then go for second approximation. Sir, first approximation I didn't get 0, then take first approximation only. I don't know how many of you understand this point. You can take the approximation such that always omega should not be 0. And remember, for every problem, first you have to check the first approximation. Means sin theta. Theta is very small, then sin theta is 0. Then cos theta is 1. Second approximation. Sin theta is nearly equal to theta. Then cos theta is 1 minus theta square by 2. So let me write here. Approximations. Now first approximation, that is sin theta, and theta is very small, then sin theta is 0. Then cos theta equal to how much? Very few people are responding. Second approximation, sin theta is nearly equal to theta. Then cos theta is nearly equal to. So all these approximations you can take such that omega should not be 0. Omega should not be 0. Are you ready? Stop. Okay, now I am taking listen carefully. Here we have two frequencies. One is a plus, another is the minus. Plus stands for what? Higher, and minus stands for lower frequencies. Okay. Higher frequencies is called optical branch. Lower frequency branch is called acoustic branch. So plus optical branch, this is the higher frequency, and minus, this is acoustic branch. This is the lower frequency. Now let me take the first one, plus. Ready? I am taking the first one, optical branch. Optical branch. Now listen please. For optical branch, omega plus square equal to, everybody come on say. Continue, continue. Ready? Yeah? Okay, so get ready. Now, as a k tends to 0, as a k tends to 0 means you are coming towards what? Origin. Origin of the reciprocal lattice. That means I want to draw the graph. That's why I am taking 2 points always. One is the origin, another is the zone boundary. Why? Sir already explained. It is enough to study the first Brillouin zone. Is that clear? That's it. I am taking k tends to 0. Everyone, theta tends to 0. Then you have approximation means theta tends to 0. You can have sin theta 0 or sin theta equal to theta. First take sin theta equal to 0. Ready? So k tends to 0 implies sin ka tends to 0. Make it 0. Okay. Then your frequency will be 0? No. Shall I take it? Omega plus square equal to, I hope everybody understand what is the meaning of that. So come on, say beta 1 by m, because this is 0 and root and square gone, so both are same. Any doubt? Is it dependent on k or independent of k? Independent. So it's constant. It's a maximum value, that too constant. Oh, it is independent of k. Super. Without doing mathematics, we don't know what is happening there. Independent of k. It's a fixed value. When for optical branch, as a k tends to 0. Okay, ma? Right. Next one. Second, I told you I will always check 2 cases, zone boundary and origin. Plus or minus pi by a. Ready? What is this, Naina? Zone boundary. Ma, sin square ka. Sin square ka. Sin? Sin? Wait. We should get minus. I mean, we should get that 4 by mm. First zone. What she is saying is right. Sorry. Which which atom it is? I mean, which lattice it is? Diatomic. Very nice. Sorry. Very good. Thank you. The tension. So why it is same? Good. It's not pi by a. It is pi by 2a. 1 second. The reason is we have taken diatomic. So what is the atom to another atom? Atom to the same atom distance is what? 2a. Everybody understand? Earlier we have taken all our same atoms. That's why atom to atom, what is the distance? A. But here small m, capital M, again small m. Then what is the distance between small m and small m? Capital M and capital M. That's why you have to take. That's good. Now take it and substitute. Ready? So sin square ka. Sin square pi by 2. Sin square pi by 2. Are you interested? You are not saying anything. Omega plus square equal to. One more time. Take this and substitute. A gets cancelled. Sin pi by 2. So come on. Whole square minus. This is nothing but a plus b whole square minus 4ab. A plus b whole square minus 4ab is nothing but Okay, right? Don't ask, is it 1 by capital M minus 1 by small m? No. Why? Small m is less than capital M. That is the assumption we have to made. So, small m less than capital M. That's it. And once it is beta 1 by m plus 1 by capital M plus beta 1 by m minus 1 by capital. So, capital M term gets cancelled. Could you please tell me what is the final answer here? 2 beta by, finally, omega plus equal to, come on I say. So, this is the optical branch properties. So, what I have taken is optical branch, that is a plus, okay, and I have taken at origin what is happening and at zone boundary what is happening. Amma listen, we have taken a diatomic lattice, that's why we have to take that lattice parameter. Lattice parameter is the distance between two identical atoms, either small m or capital M, that's why it is 2a. And finally we got this at zone boundary, what is the frequency? Under root, come on. And then write the conclusion. Optical branch at origin at k equal to 0, omega is 2 beta, omega plus equal to under root 2 beta into 1 by small m plus 1 by capital M, which is independent of k. At k equal to plus or minus pi by 2a because of diatomic atom, diatomic lattice, it's a 2a, and your omega plus equal to under root 2 beta by a small m. This is the conclusion of optical branch. Next we need to take acoustic branch. The same study we have to do, approximations at zone boundary as well as at the origin. The higher frequency branch is called optical, and the lower frequency branch is called acoustic. If you remember, this was your CSIR 5 marks question, but we have done in the quantum mechanics. Just write the conclusion for optical branch. So at the origin, we got the frequency independent of k, which is a constant. And at a zone boundary, we got the frequency as under root 2 beta by small m. Just remember that. Ready? Yeah? Now take the acoustic branch. Again take the approximation. First one, k tends to 0. Please take approximation. Which approximation you want to take? First or second? Check it out first. First take first approximation. That means what? K tends to 0. Listen, stop. Ready? Yeah? So k tends to 0. Come on. Sin Ka is also tending to 0. Then this is 0. This and this value both are same. Then what you are getting? 0. Oh, that implies omega equal to 0. Is it acceptable? That's why I am going to the next approximation. Sin theta is nearly equal to how much? Come on, do it. Simplify. You have done in the quantum mechanics. Group velocity. Yeah, take it and simplify. Just take out common. Don't get tension. Just take this term out. Then again take common. First bring this 1 by small m plus 1 by capital M whole square, bring it out, take common, and again take common. From that root, first bring that 1 by small m plus 1 by capital M whole square out. Minus beta, just bringing outside. Don't copy, don't copy. Letter to letter, if you copy without knowing this, no use at all. So here it is 1 minus 4 by small m capital M. It is k square a square. But you have taken this common. You have taken that common. That's why it will be how much? Please check carefully. Small m capital M by small m plus capital M whole square. Why? Reverse you have to multiply because you have taken common. Please do it, please do it. That is also your previous CSIR question. If you take this common, 1 by small m plus 1 by capital M, which is nothing but small m plus capital M by small m capital M whole square. That you have taken common, but here it is not there. That's why into reverse small m capital M whole square by small m plus capital M. Now cancel. Oh, cancel this term. And finally you can take out common. 1 by small m plus 1 by capital M taken common. Here 1 minus. This term is also came here under root 1 minus 4 k square a square small m capital M because of its square by small m plus capital M whole square. Apply the binomial expansion because the Ka is very small. K is tending to 0. This is very small. That's why take the binomial expansion. 1 minus. This is a whole power 1 by 2. That's why 1 minus, I think you got 2 k square a square small m capital M by small m plus capital M whole square. Then this 1 gets cancelled. And surprisingly, here beta 1 by m, 1 by capital M into 2k square a square small m capital M by capital M plus a small m whole square. Now again simplify. M plus a small m, it will be cancelled, and mm also cancelled. Finally, I think you got 2 beta k square a square by capital M plus small m. Check it out. And omega minus, final answer, you can write it as Ka under root 2 beta by small m plus capital M. Oh, surprisingly, it depends on K, dependent on K. So, as it is approaching to the origin, your omega value depends on K. Now take the zone boundary. I hope I need not explain this. K tends to plus r minus pi by 2a. This 2 is because of diatomic lattice. Same thing, substitute omega minus a square. I hope you are copying. Same logic, beta 1 by small m plus 1 by capital M minus beta, this time 1 by small m minus 1 by capital M, but here minus is there. Earlier you have plus, but here minus is there. That's why what is cancelled ma? Small m cancelled. That's why 2 beta by capital M. That's it. Now take the conclusion. Acoustic branch. At zone boundary, K tends to 0, omega minus equal to Ka under root 2 beta by a small m plus capital M. This is your CSIR question. They asked what is the group velocity, that is a d omega by dk. And at a zone boundary plus r minus a pi by 2a, you got omega minus equal to under root 2 beta by capital M. But remember, capital M is greater than a small m. If you simply copy, there is no use, because whenever you see a question you can't identify, that's the problem. Or although you know the solution, you can't attempt with confidence. These are the two negative factors if you simply copy and write. Just wait, relax. Galaxy spelling it. Galallaxy. For example, one person taken this second class or third class student taken, the teacher given the fill in the blanks of galaxy spelling. Gone. Who it's yours, sir? Right. So till now what we have done is, we have taken a diatomic 1D lattice and right. So we find the dispersion relation. That dispersion relation contains the two frequencies. One is the higher one, another is the lower one. So corresponding to the higher one we call it as an optical branch, and the lower one is called so what is these branches? Phonon spectrum. Phonon means simply the minimum amount of energy absorbed or released during lattice vibrations. Amount of energy absorbed or released is common everywhere. So during lattice vibrations, that refers a phonon. Then what is a photon? The photon is also minimum amount of energy released or absorbed during electron transition. So that's the difference between photon and phonon. Somebody attend one interview, they asked, what is the difference between phonon and photon? They said TN. Not understood, so they didn't say like that. So what is the difference between photon and phonon? Photon stands for the amount of energy released or absorbed during electron transition. Which electron transition? Valence electron transition. Hey, why nice? Inner electron transition, what is the problem? X-rays. Inner electron transition stands for X-ray spectrum. Valence electron transition, only valence electron transition is the gamma spectrum, that is photon spectrum. Next, phonon means what? The minimum amount of energy released in the lattice vibration. And the next one, photon travels with velocity of light c, and a phonon travels with velocity of sound. Phonon travels with, photon travels with, that's the difference. Is that clear? Good. And after that, K formula, energy formula, everything is the same. Whatever you have written for photon, you will write the same thing. Only the difference is velocities are different. Expressions are same. Velocity here it is velocity of light c, and there it is velocity of sound. Clear? Ready. Now here we are discussing a phonon spectrum. For 1D diatomic lattice. Amma, very important, please listen. And this indicates continuous or discrete? Continuous nature. Right. And here we have already got two things. First one is optical. Sorry, first one I will take acoustic. First I will take acoustic. So just now I got, could you please tell me what is acoustic? K tends to 0, what is omega minus, come on say. Beta varaku okay, after that sound intensity decreased. Next, K tends to plus or minus pi by 2a, zone boundary, omega minus equal to under root. Good. And after that, once again I am writing this, optical branch. For my explanation I need, that's why I am writing Amma. So K tends to 0, this omega plus is equal to, it is independent of under root 2 beta. Oh, okay. 1 by small m plus 1 by capital. And a zone boundary plus or minus pi by 2a. This omega plus equal to under root. Remember one thing, whatever the lattice you have taken, diatomic, that is a small m and a capital M. Maybe in the beginning I forgot to mention that capital M is greater than small m. Common sense, that's why we have written like this. Very nice. Now I am taking the spectrum. This is omega. This is the K axis. So from the study of the first one, we have understood it's enough to study only first Brillouin zone. Here the Brillouin zone boundary minus pi by 2a. So this is the first Brillouin zone. Ready? Okay, so as usual, let me take the first one, acoustic branch. Just you have to take the points, one is at origin, another is at the zone boundary. At origin, put K equal to 0, how much? 0. Now these are zone boundaries. Right. At zone boundary, omega minus is and some value. So this is under root. Okay. So here it is 0, and at this point this is the value. That's why I hope everybody understand. Any trouble? Say yes or no. Right. So this is the acoustic branch. At K0 we have the frequency 0. At K equal to zone boundaries we have under root 2 beta by capital M. Good. Next, come to the optical branch. This is omega minus over omega minus Which branch it is? Acoustic. Now optical branch, at k tends to 0, your omega plus is independent. That means is it a constant? It's a constant. How much it is? Under root 2 beta 1 by m plus 1 by capital. Otherwise m plus m by small m, anything you can write. That's good. Next come to this. At zone boundaries, under root 2 beta by small m. Now we got it out. Under root 2 beta by capital M is large or under root 2 beta by small m is large? Small m is less than capital M. That's why under root 2 beta by small m is greater than. That's good. So for another branch, at the zone boundaries, you are getting a value which is slightly above this. Say yes or no? So that's why so at here it's a maximum and decreases to this value. Maximum decreases to this value. Now if you carefully observe, this is the phonon spectrum corresponding to optical branch and this is the phonon spectrum corresponding to acoustic branch. Acoustic kaadamai, acoustica. Right. So finally what you observe, there is a gap. Is there any energy transmission in this gap? That means here what we are having a forbidden energy gap. Okay. So this is the forbidden, no energy transfer, forbidden energy gap. That's it. Okay, so this value is under root 2 beta by capital M and this value is under root 2 beta by small m. If I don't want forbidden gap, what shall I do? Small m equal to? If small m equal to capital M, do you have this? If small m is equal to capital M, will you get this? No, it's a Debye lattice. Debye lattice and one atom. Debye lattice, one atom. Or masses are same, different atoms. For example, masses can't be same, huh? Any two atoms are having same mass? No. Any atom as having same mass? Or no. A different atomic number, different mass numbers. Okay. I mean isotopes or something like that. Anyhow, if masses are same, then only this band gap will be 0, energy gap will be 0, otherwise there will be energy gap between optical branch and acoustic branch. That's it. This is the phonon spectrum. Come on, draw it. You please write those points what I explained. Phonon means travels with velocity of sound, photon travels with velocity of light. Difference between phonon and photon, right somewhere. Energy, same formula, H cross omega. And what is that? Momentum, H cross k, no change at all. But the velocity of a phonon is velocity of sound. What exactly phonon is? Quanta. The quanta of lattice vibrations. A single word, lattice vibrations. Quanta of lattice vibrations. If anybody asks what is the difference between photon and phonon, You just say that is the travel with the velocity of sound, phonon. Photon travels with velocity of light. Optical branch, how it oscillates. Just I am giving the diagram. If you want derivation, please see the textbook. I have derived, but there is no time. So this is for optical branch. The two atoms are there, one is A, another is B, you know, small m and capital M. So both are out of phase. They vibrate out of phase. This is also a very important question. But for acoustic branch, they are in phase. They are in phase. So A, B, A, B, A, B, A, B. If you want derivation, just see the textbook. I came with the derivation, but there is no time. We have to finish one more small concept, and after that tomorrow we will go to very most important thing. That's why here this is A and this is B and A, B, something like this. So here vibrates in phase. Vibrates in phase. Please draw the diagram properly. So I am not explaining this, only this one. So there is a small derivation. If you see the textbook, for acoustic branch they will prove that A by B equal to +1, and for optical branch they prove that A by B equal to minus capital M by small m, a reciprocal of the ratio. I am writing here A by capital B equal to minus capital M by small m. That is the reason why they are out of phase. Please write this and draw the diagram properly. And if you want, please write the sentence. In optical branch, the two atoms are vibrating out of phase. In acoustic branch, the two atoms are vibrating in phase. If you want derivation, it is in the book. Still, if anyone is not understanding, please ask me. Nothing, you have to take the while you are finding the determinant, you have written two equations A and B, check. In those A and B, you have to use the approximation. What approximation? K tends to 0 approximation you have to use, okay. Whatever you have taken in the acoustic and whatever you have taken in the optical, you have to use a K tends to 0 approximation, and then you will get that result. But that is a very important question, and they will ask you in interviews also. Be careful. How the atoms are vibrating in that acoustic branch and optical branch. Optical branch out of phase and acoustic branch in phase. Or else I will send that derivation. If you want, you can write in your notebook. I will send after the class. A small derivation is there, ma. I will send after the class. If you want, leave one space. Those who want to know how it is out of phase, how it is in phase, just leave one side. There is a small derivation. I will send. You can write. Ready, stop. So this is also given in CSIR, and most of the times given in the GATE exam, but very important. Listen carefully. So here we are discussing this phonon spectrum. Listen, very important. Phonon spectrum. Phonon spectrum of non-Breve lattice. Non-Breve lattice. Non-Breve lattice means it is having number of lattice points per unit cell more than 1. So yes or no? Wait. Very important. So this means what? The number of lattice points. The number of lattice points per unit cell. Per unit cell is greater than 1. That's why I am taking it as a P. Number of lattice points per unit cell is a P. Now we have to find the branches. So you are getting two branches. One is the acoustic branch, another is acoustic. Also there exist multiple modes, 3 acoustic branches, 4 acoustic branches, like that. They may exist, but here we have taken only 2 atoms. That's why we got 1 acoustic, 1 optical. Is that clear? If it is a 4 more atoms, 5 more atoms, 6 more atoms, then the number of modes will be also increasing. Wait. All of you, please listen. Very important. The phonon spectrum of non-Breve lattice, that means the number of lattice points per unit cell is P. Then the total modes, the total number of modes, the total number of modes, 1 second, okay, the total number of modes, I am talking about the total. is always equal to D, D for dimension, into P, P for number of atoms per unit cell. D for dimension. Now come to this. Now I am taking D for dimension, and this is the number of atoms. We have taken number of atoms as P. Now I am taking the one dimension, that's why total modes. I request you please say total modes of vibration. It is a one dimension. How much? P. And this total modes, two types are there. Already we have seen. One is acoustic, another is optical. Okay na? Next, if I take a two dimension, that means a 2D lattice. Very important, amma. Come on, I say the total modes of phonon spectrum. The total modes of phonon spectrum 2p. Again, this is having acoustic branches, number of acoustic, as usual, number of optical. Are you listening? Next, 3 dimension, total modes, and total modes of phonon vibrations. How much? 3. And again, this is having number of acoustic, and this is having a number of optical. There are 3 atoms. There are 3 atoms. Then, how many total modes of vibrations exist? 3 into D. If it is a 1 dimension, 3. If it is a 2 dimension, 6. If it is a 3 dimension, 9. That is the total modes of phonon spectrum. Out of that, some are acoustic, some are ready. Number of acoustic is always equal to dimension. Acoustic. The number of acoustic is a dimension. How much? 1. Remaining is optical. Let us apply this to 1D monoatomic lattice. Yesterday you have taken 1D monoatomic. Ready? How many atoms? 1 atom. 1D lattice. Then the total modes. 1 into 1. Super. Acoustic. That's why in the yesterday's class we got only the lower one. Am I right? Okay. Next. Acoustic, number of acoustic equal to 2 dimension. Then optical. More 2p minus 2 kaadu 2p minus 2. Okay na? Ready. Next. Acoustic. Optical. Now there was a CSIR question. The question passage is around half page length will be there. Okay, I have written that question also. Something like this. This is the question. And is asking number of optical phonon modes. I will draw that diagram. This was the previous CSIR question. Then you will understand why I explained this table. So they have given this cubical structure, something like that, and what they mentioned is at the corners they have a Ba2 plus atoms. At the corners they have Ba2 plus. At the 8 corners we have a Ba2 plus. This is a Ba2 plus. Are you observing? After that they said the phase centers O2 minus. Phase centers O2 minus. Phase center, and phase center. Total 6 phase centers. So this is O2 minus. That lattice name you want, barium tritonate. BaTiO3. Barium BA అందరూ తెలుసులే తర్వాత after that leave it. edged. And one more in the center, that is Ti2 plus. Ti2 plus. Like this they have given, the diagram also they have given. And they are asking what? The number of optical phonon branches. They are asking number of optical phonon modes, not branches, modes. All of you please listen. First you have to find number of atoms. Yes or no? Let us find the number of atoms. 8 corners naina, sharing is 1 by 8. Amma face centered 6 amma 1 by 2. In the middle, so 1 plus 3 plus 1. How much? Is it a 3 dimension? Or more? Cube, 3 dimension. So that's why total modes equal to 5 3s are 3 5s are 15. In this 15, I told you already, acoustic is always how much? Dimension acoustic. Then optical. Ante. Huh? What? Say? What happened? You said 6 answer. I heard that, but time up, that's why I didn't say anything. Somebody said 6. It's okay. कभी कभी ऐसे होता है. Offline. I'm sending that. Rajkot is in Gujarat. Oh, that's it. I send those derivations to your WhatsApp. If you are interested, please write those derivations. How that A by B is minus capital M by small m, and how this A by B is a plus 1 I have derived. I send that down small derivations. How many lectures over? 7. No, 7. 7 lectures. 1 day missing. So the number of total modes is dimension into number of atoms. So acoustic is always equal to dimension. That also please write. Acoustic, number of acoustic is always the dimension. This is equal to the dimension.